Okay, so we began discussing example 14 in class, and in this video I just want to supply some of the details that we didn't provide there. So what were we trying to do? We're trying to show that the set of positive integers z is countable. And to do that, we need to find a bijection from n onto z. So we were trying to show that z is countable. In other words, there's a bijection from n onto z. So that's what we were trying to find. And so what did we need? We needed a bijection, in other words, a one-to-one, and surjective, or onto map f, mapping n onto z. And essentially, if you're trying to show that a set is countable, what do you need to do? You want to be able to list all the elements in that set as an infinite list in such a way that no terms in that list are repeated, and in such a way that all the elements in the set actually show up eventually on that list. And we could list all the elements in Z and obtain every single element in Z. In other words, we wouldn't miss any element in Z if we listed them in this way. We start at 0, and then we alternate between positive and negative numbers. 1, -1, 2, -2, 3, -3, 4, -4. And we can see that certainly we're going to obtain all of the integers in this way. Well, we want to be more precise in terms of our definition of countability, so we'd like to actually have a bijection from n onto z, and to do that, well, 1 maps to the first element in our list, 2 to the second element in our list, 3 to the third element in our list, and so on. And that defines our bijection. But, of course, this is pretty good, and we can clearly see that z is countable at this point, but in this class we want to learn to be mathematically precise, and so we want to have a specific formula for our function f from n onto z, and we thought that this should work well. Did this in class. We said, well, if you notice, the even integers, or the even positive integers, the even natural numbers, are mapping to the positive integers, and our odd numbers were mapping to our negative numbers, and also to 0. And we noted that this formula here would work. So even number 2k maps to k, and odd number 2k plus 1 maps to minus k. This seems to describe this function up here, as we noticed in class. Well, clearly f is well defined. What does that mean? Well, every natural number is either a even number or an odd number, and can't be both, and we've defined f at each even number and each odd number in a very precise way, so we've certainly defined a function f from the natural numbers, the positive integers, onto z. Okay, so f is well defined. We want to show that it's a bijection. It certainly looks like it's one-to-one. Distinct points in n are mapping to distinct points in z, and it certainly looks like it's onto, as we said already, but also we want to be precise in this class, so we want to explicitly show that f is a bijection. Alright, so what's involved in doing that? Well, we need to show that f is both one-to-one and onto. So let's do that. So first, we'll show that f is onto, or surjective. So how are we going to do that? Well, to do that, we are going to take an arbitrary element k in z, and what do we need to show? Well, we want to prove, or it's enough to prove, want to prove that there exists some n in n such that f of n is equal to k, right? that's what it means to say that f is onto each element k and z is the image of some element n in our domain, which in this case is the set of natural numbers. All right, well, we have two possibilities. If k is greater than or equal to 1, well, then n equal to 2k is a natural number, a positive integer, and in this case, we have that f of n, well, that's f of 2k, and what is f of 2k? Well, f of 2k is just k, which is what we needed. All right, look up at our formula, and you see that f of 2k is k. All right, so now what? If, on the other hand, k is less than or equal to 0, well, then certainly n equal to 2 times minus k plus 1 is going to be a positive integer, right? K is less than or equal to 0, so minus k is greater than or equal to 0. Multiply by 2, greater than or equal to 0, and add 1. We have a positive integer at least as big as 1. All right, so in this case, n equal to 2 times minus k plus 1 is a positive integer. And from our definition, f of n is equal to, well, it's f of 2 times minus k plus 1, which, according to our formula, is equal to the negative minus k, which is equal to k. So, in any case, regardless of what k and z we are given, we're able to find an n and n such that f of n is equal to k. Note that if you give me this k, it's either greater than or equal to 1 or less than or equal to 0. Either way, we found an n such that f of n is equal to k. All right, so the next thing that we need to do is show that f is 1 to 1. In fact, that's the last thing that we need to do. So f is 1 to 1. So for this, we're going to suppose that f maps m and n to the same value, and what we want to prove, or what we want to show, is that m equals n. Alright, if we've done that, then we'll have shown that f is 1 to 1. Okay, so two cases. Either this common value, f of m equal to f of n, is a positive integer, or maybe it's less than or equal to 0. So first, let's suppose that this common value is greater than 0. Well, if it's greater than 0, then what can we say about m and n? What can we say about m and n? Well, if you remember, only even numbers, m and n, get to map to positive values. Odd numbers, m and n, are mapping to numbers that are less than or equal to 0. So if f of m which is f of n, is positive, it must be true that m and n are even. All right? So we can say that. So then, m and n are even. All right, so let's say m looks like a 2k, and n looks like a 2l. All right, for some k and l. Well, then, what do we know? Well, we are assuming that f of m is equal to f of n, which is to say, because n is 2l, so f of 2l is equal to f of 2k, but if you look at our formula, f of 2k is just k, and f of 2l is just l. So what do we have? We have that k equals l. So that means that 2 times k must equal 2l. In other words, m equals n. So let's just write that down. So m, which was 2k, must be the same as 2l, which is n. Alright, which is what we needed. So in this case, if the common value of f of m and f of n is bigger than 0, we are able to conclude that m is n. Alright, the other case is that this common value isn't bigger than 0, in other words, it's less than or equal to 0. So let's see what happens then. Alright. So, if f of m, which is f of n, happens to be less than or equal to 0, well, then it's only odd numbers, m and n, that are mapping to integers that are less than or equal to 0. So then we can say m and n are odd. Alright, so say m is equal to 2k plus 1, and n is equal to 2l plus 1 for some k and l greater than or equal to 0. But then, what do we know? Well, again, we're assuming f of m is equal to f of n. There it is, f of m is f of n. And n is 2l plus 1, so this is f of 2l plus 1. M is 2k plus 1, so this is f of 2k plus 1. What is this equal to? This is equal, by definition, of our f to minus l. This is equal from our definition of f to minus k. Alright, so we now have that minus k is the same as minus l, therefore k equals l, and therefore 2k plus 1 is going to equal 2l plus 1. Alright, let's write that down. So, k equals l, and therefore 2k plus 1 is equal to 2l plus 1. That is m is equal to n. Alright, so in this case as well, if f of m is f of n and this common value is less than or equal to 0, again we got that m is equal to n. So in particular then, in any case, if f of m is f of n, we've shown that m is equal to n. This shows that f is 1 to 1. And we've now shown that f is both onto and 1 to 1. That means that our f is a bijection. Our f is a bijection from n. Our f is a bijection from n onto z. That means that z is countable. That's what we wanted to prove.